Hi. Chapter number 2, we'll talk about Earth-Sun relationships with solar energy, the seasons, and the atmosphere. When we talk about the sun is the most important entity in the solar system. Without it, we'd literally be nothing. But it's Milky Way. We're part of a galaxy of about 400 billion stars, and there's a number of other galaxies out there. So it's, in terms of uniqueness, the sun isn't unique in any way, shape, and form. When we talk about the Earth's orbit around the sun, it makes an ellipse, which is a slightly elongated circle. You can see it here. There's a mathematical formula applied to it here, but you can see the shape of this ellipse here. It's slightly exaggerated. At perihelion, it's at about 91.5 million miles when it's closest. Aphelion, when it's furthest away, it's about 94.5 million miles, and we generally talk about the term 93 million miles away. The interesting thing is that the sun is closest, or the Earth is closest to the sun in its orbit every year, January 3rd. Well, January 3rd, it's relatively cold. In other parts of the world, it's hot. So we'll talk about some of the reasons why that is. You can see the solar wind, and then we have the Earth magnetosphere. So previously we talked about the biosphere, the atmosphere. Outside of that, we have this magnetosphere, and as a result, we have the aurora borealis in the higher and lower latitudes. And we have a number of satellites that monitor the sun, all the forms of the EM, electromagnetic radiation, that comes from the sun. And it's monitored through a variety of different wavelengths. Previous chapter, I showed a remotely sensed image of Baltimore, what we call false color, meaning these are wavelengths that our eyes can't see. This EM spectrum, we have solar bands, EM, concentrated in your ultraviolet, your visible, and your shortwave infrared. But the main point I want to portray is that the sun gives off lots of different wavelengths. What we see is just a very tiny portion of those. But this insolation, the incoming solar radiation, is it varies. It's not evenly distributed around the planet. And these are just an example of some of the wavelengths here. We've got microwaves. We know what a microwave is. Thermal infrared, like heat lamps, basically heat. Near infrared, UV, X-ray, gamma waves. So you can look at the different wavelengths of these, and these are all in terms of micrometers, they're all relatively small. You can see visible light, right? And so you can see this is Camden Yards here, this is your Inner Harbor here. This is what our eyes see. But there's lots of other instances that our eyes can't see. This is St. Peter's Basilica in 2002. So there's a relationship between the sun and the Earth, and in terms of intensity and wavelength. This false color image we can see here. This isn't what our eyes can see. I believe this is some of your near infrared. So typically your red or your more intense red shows stronger near infrared. And typically we use infrared to detect healthy vegetation. We might see two plants that are green to our eyes, but if it gives off more or reflects more of your near infrared, it highlights that it's healthier than other. Here, this is, I believe, Mount St. Helens. And I believe this is some other false color imagery to some extent. Definitely false color imagery. Solar energy is typically transferred to the upper atmosphere and can influence global atmospheric conditions, disrupt EM carrier waves, satellite communications, power grids, or whatnot. Our subsolar point, the location on the Earth's surface that receives direct solar radiation. The Earth is tilted at a 23.5 degree angle, so the sun will never be directly overhead in Virginia. Okay? So it vacillates or oscillates between 23.5 degrees north latitude and 23.5 degrees south latitude. So your Tropic of Cancer and your Tropic of Capricorn. That's where they get the direct solar radiation. Okay, so in a little bit I'll talk about the angle of the sun and how that affects incoming solar radiation. So you can see this incoming solar radiation. You can see at the poles or places near the poles, it gets more direct radiation versus at these oblique angles. This is at the equator versus at the poles. So at the poles, it gets this oblique radiation. At the equator, it gets this direct radiation. And I'll show an example of this here in a second. So this sun coming in can hit at direct angles or oblique angles. Okay? And it gives off more, basically it has more energy, it's more concentrated than others. You can see your net radiation patterns, and obviously places near the poles get more direct radiation. Places at the equator get more direct radiation than at the poles. Okay? So you can see the amount of incoming solar radiation, this insolation that we talk about. There's lots of other things that can happen to incoming solar radiation. It can be reflected, absorbed, scattered throughout the atmosphere, because we have constituents of the atmosphere or whatnot that when it interacts with this incoming solar radiation, depending upon the wavelength, it can reflect back to Earth, or it can make it all the way to the surface of the Earth. So we've got a revolution, we've got a rotation. So revolution, the Earth orbits the Sun every 365.24 days. What do we do at this 0.24? Well, it's leap year, and actually my birthday is on leap year. And in years of 2100, 2200, 2300, we don't have a leap year to make up for this little 0.4. The Earth rotates on its axis every 24 hours. We call it a day. The length of the day is affected by the change in position of the Sun during its revolution. I'll show a couple examples. But you can see at the poles we have direct, at the equator we have direct versus at the poles. So you can see the same amount of radiation is being spread out over a larger area, which is going to make it more diffuse. You can see the relationship between the Earth, the Moon, the Sun, and then you can see this tilt here, and then the perpendicular with relation to the ecliptic. That's the path that the Earth takes around the Sun. And then, depending upon how far north or how far south you are, you can see the length of the day on certain dates here. I'll show a little example here. Last summer I went to Iceland, and hopefully you'll be able to see this. But I went there just after the summer solstice, just south of the Arctic Circle. So on January the 26th, this is a neat site called timeanddate.com. I typed in my location. I was in Iceland. I was there about the 26th. The sun rose at 2:58 a.m. It set at 2:02 a.m. So it's kind of interesting how short the day is. Now, what do you think is going to happen if I type in a date soon after, around Christmas? It's going to be the entire opposite. The sun's not going to rise till about noon, and it's going to set about 3 p.m. So it does even out. Places near the equator, they get 12 hours of sunlight every single day of the year. Places near the poles are much more extreme. So you can see the relationship here at your equinoxes versus your solstices. In the northern hemisphere, if we're at about 40 degrees north, we get about 15 hours of sunlight. You get further and further north, 18 hours of sunlight. June 21st, we were at about 64, even more than that. Okay. And this is actually a picture taken from my hotel room at about 10:30 at night in Iceland, Reykjavik, Iceland. Yeah. I thought this was kind of interesting because they have these black shades that they put down over because the sun's still out. And then I woke up the next morning at about 3 o'clock to get my flight, and I didn't even need a flashlight or anything. So this is the big famous opera house I think it's called Harpa Opera House in Reykjavik, Iceland, at about 3 in the morning when I went running. We have seasons, so December 21st is what we call the winter solstice, where the subsolar point, the sun's directly overhead at 23.5 degrees south latitude. We have equinoxes, that stands for equal night. The subsolar point is at the equator, where the sun's directly overhead at the equator. And then June 21st is what we call the summer solstice. Sun's directly overhead at the Tropic of Cancer. So the sun will be highest in the sky in Iceland at that point in time, but it'll never be directly overhead. So even though the sun's going to be out for 18, 20, 21 hours, it's still going to be getting this indirect sunlight. And you can see what's happening as the Earth goes around the sun. Basically, we have this circle of illumination with the Arctic Circle. So places at December 21st, this circle of illumination, the Arctic Circle is always going to be on the dark side of this circle of illumination. And you can see a cross-section of it right here. This is what's happening right here. Okay, and it's going to be total opposite in winter, where in the southern hemisphere, the South America, Australia, they experience their summer while we experience our winter. These are equinox conditions here, and then these are at your solstices. So you can see your Tropic of Capricorn. Like I mentioned before, your sun angle. Okay, so like I said before, in Virginia, the sun will never be directly overhead. June 21st, it's going to be the highest it will be in the sky. If we're at about 40 degrees north latitude, that goes through Trenton, New Jersey. It'll be about 73 degrees. It'll be a little bit more since we're a little bit further south. And like we said before, the Earth's orbit is not quite elliptical, but after this talk here, I think we have a good idea as to why that is. Okay, and it's not because of aphelion and perihelion. And then you can see seasonal vegetation to the migrating sun as we look at those.